Okay, so yeah, thanks Wendy for inviting me. Thanks you all for coming out. I'm not going to talk for long because I know you all want to go and try out Token Card in the pub, so I'll keep it short. So I just need to just mention what who I am. I run a consultancy in Oxford called Extropy. We do blockchain development, security audits, etc. What might be more interesting for you is that we also, along with a partner, run a number of workshops for developers. So pretty much every weekend now we're running some workshops. Certainly if you're interested in zero knowledge proofs, we did a zero knowledge proof workshop last weekend, and we plan to hold these pretty much every month. So if you're interested in any of those, they're all free. I know some of you in the audience have already been to some of them, so just get in touch with me or check out the website and sign up for those. Okay, that's enough about me. So this is a talk about a consensus mechanism, and it was developed along with this company, Zane. I was working for them. They're a Berlin startup, so I worked with them for a couple of years. So this is not new, I'm afraid, but because the last meetup you had Silvio Micali from Algorand talking about how Algorand works, and because this consensus mechanism borrows a lot from Algorand, I thought it might be interesting for you to see what we have done with it. So we wrote a paper about this. If you're interested, you can look it up. It's on the Royal Society Open Science website. So it started off because the CEO of Zane, he was very much in favor of proof of work. But one of the problems that people have with it, especially because we were looking at the time at small devices that we wanted to run nodes on. One of the problems with proof of work is that the amount of energy, I mean, here's maybe slightly out of date now. I think this was true a few weeks ago, but Bitcoin network was taking the same amount of energy as used by Uzbekistan. So we're looking at how could we develop a different mechanism that would use less energy, because we were targeting small devices. We were targeting devices to put into vehicles, so we were trying to find something that would use less energy. And we came up with this thing called Proof of Kernel Work. I don't know where the name came from exactly. It was the CEO who thought of that, but it had to be called Proof of something, and then the rest of it followed. And we came up with a two-stage mechanism. And I should point out this was for private networks. This is not for a public network. This is for private networks on Ethereum. And it's a two-stage mechanism. We start off with a whitelist of nodes who are interested in mining. And from that, we select a committee. And then from the committee, we then select a winner who will produce the next block. The selection of the committee is done via cryptographic sortition, which is the part we got from Algorand. The selection of the winner from that committee is then just basic proof of work. So quite a simple idea. The cryptographic sortition, the features you need for that is that the nodes need to know themselves whether they have been selected for the committee. So this runs for every block. There's a new selection of a committee. So the nodes need to be able to determine themselves whether they have been selected. And then the other nodes in the network, when they're verifying the blocks, need to be able to verify that the miner that produced the block was actually on the committee. And this also then involves some kind of identity. So we need some private keys involved here, or some identifier for the nodes. This is based on some work. Again, we got this from Algorand. Verifiable random functions, nice things, where you take a key, a secret key, and a seed, put it through your function, and it gives you some random output, but also proof of that output. And then other nodes can take the random output and the proof, and the public key corresponding to the secret key, check that, and decide whether that was actually the correct output from the function. So, okay, quite straightforward. This is what used by Algorand. So their algorithm for doing sortition is this. So quite complex, but they take the seed and then the role also and the secret key. So the role is because they permission things differently, and produce a hash. This is the random output, and a proof. They then also weight the chance of getting into the committee is also weighted to do with the number of tokens you own. I know when from the talk the last meetup, some people didn't kind of like this idea and wanted more the idea of kind of one account, one vote or something, but it's quite difficult to do this in a way that is Sybil attack resistant. Anyway, so this is the algorithm from Algorand. So this is much more complex than the one that we went with. This is a slide that Xane produced to explain what we were doing. There's a slight mistake on it. This is not quite true here, but I think the basic idea is fairly easy to follow. So we're producing blocks. Each block has a seed. We produce this function and do the sortition. And there is a mixture of some public information and some private information. So you're getting private keys from the various nodes here, mixed with the public information of the block seed. And from that, we can do the sortition function to decide whether each one of these nodes will be selected to be on the committee. So we've colored the ones green here that were selected, and the one in sort of purple has not been selected. And then we go to the next block, and we just repeat the same process. The actual formula we use, and there are various options for this. What we have done, we take this seed from the previous block, so R here represents the block height. And then from that, you can do it in two ways. You can either sign that to get your seed for the current block. The other thing you could do is to just do a hash here. If you're doing a hash, that's quite nice because it makes it deterministic. So if you imagine you're a node using this protocol, what you could do is you could work out going forward just by going through hashing the seeds repeatedly. You could work out for the next, say, 1,000 blocks what the seeds are going to be, and then you could work out using your own private key whether you will be selected for the committee. And if you're not going to be selected for another 500 blocks, say, then you could go offline and then come back when you are going to be selected and take part. If you do it by signing, that makes it perhaps a little bit harder to attack. So a malicious attacker would not know in advance what the seeds are going to be. Then the actual sortition itself, is quite simple, really. N here represents a target committee size, and this is the total number of nodes that are in the whitelist. So we're just taking a percentage of the whitelist size and saying we're going to have that, that's going to be our threshold. So say you've got 16 nodes altogether on your whitelist, and you want to target a committee size of 8, then you're going to get 50% here. And then we take the seed for this block, block height, we just sign that with our private key, so that's where our private information comes in. And then we apply a hash function to that, and then normalize this between 0 and 1, and then test that against the threshold. So I think that's quite simple, quite straightforward. And it means this, that just tells you if you're lower than that amount, then you're a member of the committee, and you can then go and do the proof of work and produce the next block. Is that all okay? Yeah. Okay. Other blockchains have done it differently. Similar things, but say Witnet, they've done it. They have kind of a reputation function involved as well, but a similar kind of thing. I think sortition is quite a generally useful piece of cryptography, so other people have used it. Nice things about this, in terms of scalability, we're always talking about a percentage of the whitelist size, so you can adjust this, and if you suddenly you want to increase the number of nodes in your network, you can still keep the committee size the same size if you like, or you can adjust it how you like. And the actual time to reach consensus is not influenced by the committee size, really. It's just the difficulty of the proof of work, so the committee size doesn't affect the total amount of energy we're going to be using. Sorry, it does increase the total amount of energy, but that doesn't increase the consensus time. Sorry. Finality, well, we're still using proof of work, so the same rules apply. So reorganizations of the chain can occur, but if you're thinking about security, although you can get reorganizations, you could start mining your own blocks, but you still have to take into account the committee membership if you're doing that. So it's not just a question of solving proof of work, you also have to do the committee membership part as well. So the security of this effectively gives you increased security for a small committee size. So you're getting this kind of security of the whole whitelist, but you're actually only doing proof of work on the nodes that are in the committee. So you're getting more security for less energy from this. If you're wanting to attack this, you would need to try to figure out which nodes, you're going to co-opt certain nodes, you're going to have to figure out which nodes are going to be on the committee for which blocks. So it makes a malicious attacker's job quite a bit harder. The original design we had for this was a little bit more complex. So we initially had some anomaly detection as well. So we had the idea of adding some AI into this. So there would be a neural network would have been trained to look for anomalies, and that would be running on a node, and that would be checking the network for anomalies, so for malicious behavior, and also for things like the difficulty of proof of work. So if we needed to increase or decrease that, and that could then interact with the parameters of the blockchain to change that. So either increase the difficulty, say, or if you found there was some malicious behavior going on, you could eventually throw people out to the whitelist. So our original design had this, and also this anomaly detection followed a similar pattern. So the node chosen to do the anomaly detection would be chosen as following the same process. We started to do this, and then it got quite complex because you have to kind of synchronize the two processes a bit. And also the clients we were talking to really just wanted this simple version and weren't really interested in the AI part as well. So that got put on hold. You probably have thought of some problems about this. I'll mention a couple, but you can come up with some more. One that we see, it's possible to get a committee size of 0. So if you only have a few nodes in your network, it's possible that the cryptographic sortition will come back and none of the nodes will have been selected for the committee, at which point your network just stops. You can't proceed, you can't produce a new block, produce a new seed, so that's it. And that is quite a problem. Yeah.
Is it also possible to have a committee slightly larger than n, or not? Or definitely?
No, and I mean, if you have, we did have a client who just wanted 100% of their nodes involved in the committee each time.
No, say you have 1,000 nodes, right?
Yeah.
Is it possible that you will have a very unlikely scenario where 8 nodes might be selected, or is that definitely?
Yeah, you could have larger than the target size. Yeah, definitely. Yeah. So yeah, committee size is a problem. Also, there's the problem that we were looking at this on private networks, and particularly with consortia who may be running their own servers. They'll be running their own nodes, each of which will have certain hashing power, and they probably are thinking that everybody's hashing power is roughly equivalent for doing the proof of work. But somebody, if they're malicious, could actually farm out the proof of work to some server that's got a lot of hashing power, and then if they're selected onto the committee, they can pretty much guarantee every time they're going to win the proof of work race. So that is another potential problem. Whitelist governance as well. We just took a very simple thing to start with, where if you're on the whitelist, you can then add other nodes. We started looking at how to set up layers of nodes and allow some kind of voting, sort of maybe using quadratic voting, so that people could form a consensus on which nodes may be malicious and then throw them off after a certain time. But that gets quite complicated eventually. The ideas we had as well was, instead of using proof of work, we thought about using maybe proof of elapsed time. We could use some trusted hardware with that. You could also use proof of authority. So you could just select your committee and then just say take it in turns to mine a block, and then you're not using any energy. You have the problem there with liveness, I guess, because you're not necessarily guaranteed that the people are going to be selected onto the committee or the ones that are going to be doing it next. So at least with proof of work, they are actually getting involved. But whatever, these are all options for the future. So our initial client, we took a fork of Geth in November 2017, just after there was a hard fork. We added this consensus mechanism in. We reduced the size of the DAG down to 64 megs because we were targeting small devices. So this was particularly, we were looking at putting these on Raspberry Pis. We put it on a Pi 3, we then put it on a Pi 0. We were trying to move it down onto microcontrollers as well. So we really needed to reduce the memory footprint that was needed. Another problem we had was that because this is on a private network, and on a public network, you get the miner of a block will put their address in the block because they're expecting a block reward, and they're not going to put somebody else's address in there, otherwise they will lose out. On a private network, and in this case where it's permissioned, you could have someone producing a block who is not on the whitelist or not on the committee, putting somebody else's address into the block and pretending that they produce the block, and then get a block getting accepted. So we had to change the block header and actually get the miners to sign the blocks before they were sent out, so that we could prove that the correct miner did actually produce the block. A little bit of benchmarking we did recently, not many nodes and a small committee size. We started about probably a fairly average amount. This is on a private network. Got up to about 600 transactions per second at one point. Then we had another client who was running this and increased the block size, got it over 1,000 transactions per second. So it increased reasonably. It was really just a question of lowering the difficulty. So we got the difficulty, as we reduced the difficulty, obviously the block time drops. So we were doing it about 1 second maybe, but then you get the problem of getting lots of uncles because of network latency. So a sort of happy medium was about 3 to 5 seconds for a block time. And then it was just a question of increasing the block size just to get more transactions in, which worked reasonably well. I think our signing mechanism took too long, and that was slowing things down as well, so we need to work on that. All of this is open source, so the paper's been published describing the algorithm. That Geth version is also open source now. I'm starting work on a parity implementation, so I'm just going to do a version in Rust instead. But yeah, it's all open source if you want to try it out, get involved with it. Future, yeah, we'll try parity version. Maybe we'll try and introduce this anomaly detection again. Although it gets quite complex, there's quite a lot involved there. We thought about doing using zero knowledge, because this act of signing and doing all the validation can get quite intensive. And so if you're ending up with a large blockchain, it may be advantageous to rather than having to repeat this computation, you can do something similar to what Coda are doing, where they're using recursive snarks to validate blockchains very, very quickly. So we may try to do something with that, just to cut down on the time that we need to take in all of our verification. Okay, that's the end of my talk. There's my contact details there if you want to get in touch, ask more questions, or you can ask questions now. Yeah, go ahead.
I'm a little bit confused because at the beginning there was like this, Bitcoin has this energy problem with proof of work, being a public network, and then you're saying that this is only applicable to private networks. Why is it not applicable to public networks?
Just this we wrote this for private networks, and we can't really whitelist things very easily on a public permissionless network, so.
No, so can't your outside circle just be everyone? Do you have to have a whitelist? Yeah, if you could have everyone, but then you get if someone's malicious, then how do you get rid of them trying to produce blocks or trying to join the committee? That's my problem with it. Is it actually doesn't seem to prevent. It doesn't seem to have a solution to malicious behavior, because
not on public networks.
Because
no.
on colluding nodes could have. So like if someone is excluded from the committee, well, they can just donate their hash power to a committee member who they're colluding with.
Yeah.
So it doesn't have a mechanism.
So that's why I was saying we need to get the governance working and look at the anomaly detection to do that, so that you can stop people. So hopefully we would want in the anomaly detection to try to detect that behavior and try to work out if the same accounts are always producing the blocks, then maybe you would try to lower their reputation and things like that.
Just to be clear, in this private network, the nodes need to trust each other. So it's
to some extent, yeah. Yeah, or you need some mechanism to try and enforce that, yeah.
Have you got any enterprise level clients that are interested in testing? And
yeah, so we do have a client who use this and have built an application on top of this, and it's a consortium. I don't know if I can say who they are, but they're like the largest shipping and haulage companies are using this for supply chain. So I think it's about to go in production soon, so hopefully it will. Yeah. Go on, Sammy. So we initially have a list of addresses in the Genesis block. And we have a smart contract in the Genesis block with some addresses in there. And that's the initial nodes that are on the whitelist. And then you need some sort of governance to then change that and add nodes in or out.
Is that down to whoever client implements the issues with that whitelist?
Yeah, exactly. So when you set up the network, you create a Genesis block and you put the nodes that you want in there. Yeah. Go on. Go on.
How do you get around some of the issues which you've identified? And how are you creating solutions for your clients?
Can you repeat the question?
So how are we getting around some of the issues we identified, and how are we creating things for the client? So yeah, we need to develop this further. So we produced this first version, which I think the security of it wasn't great because it still does have some potential problems, and so we need to look more into particularly things like the governance and anomaly detection to get around this. Yeah. So you had.
In terms of outcomes, how is this different to something like POA? Because you also have a whitelist there, right?
Yeah.
And also rental.
Yes, I mean it's quite similar. This is just something we wanted to try this. It's relatively it's from quite a while ago, really. We like proof of work, so I think we feel very secure about having that still in there. And cryptographic sortition seems a very neat solution, so it seemed a good fit. But yeah, you could put proof of authority in there. But then you do get the problem, I guess, of the liveness that you may end up with. You may end up choosing a node that's not actually going to do anything and produce the next block. Although we also have that problem with the zero committee size. So yeah.
On a private network,
Yeah.
what problem are you solving that you couldn't do with a SQL server cheaper and quicker?
So where I've seen it used, now sometimes I think it's perhaps overused, but where I've seen it used is particularly with consortia, where they have some companies come together, they may be competitors, they want to share some information, they don't really trust each other completely, so this is a way for them to do that. Okay, this is a way for them to do that, and to be confident in how the information, whatever they're sharing, how they're going to be confident about that, or how the transactions are verified. It doesn't always make sense. Particularly, we've had instances where there's between one company who decides to set up a network, and to me that doesn't make so much sense. Although I also have known companies who don't trust their departments, so they effectively you've got a kind of consortium of departments, so they're all a little bit distrusting each other. So yeah, I see what you mean. Yeah, Steve, go.
I mean, have you implemented it so it's a pluggable consensus? Because Ethereum now's got this pluggable consensus mechanism.
Yeah.
So that once Ethereum rolls forward, we could take yours and just plug it in.
Yeah. So no, we haven't, because we started this, back in about 18 months ago. Before I think so.
Is the intention to try to do that? Or?
Yeah, if we can get the funding to do it. Yeah. I'm not sure how. I mean, this is still work. We're still looking at proof. I'm not sure how it's going to work with as Ethereum goes forward into 2.0 and things. I don't know. But we can try. Yeah.
You mentioned sort of proof of work and or proof of was it authority?
There's also sort of proof of elapsed time as well. So yeah.
Is there any advantage? I don't know. If it's possible, doing a switch up mechanism so you could switch the proof, randomize it or something that would stop someone coming in and just doing.
Yeah, that's a nice idea. I guess you might have. Yeah, I don't know how. Yeah, I like the idea.
What would it take you to take your brain power to think about how to solve these problems on a public blockchain? Because that's where we space. Because as Algorand guys, we're talking about permissionless stuff. Like, I don't understand any of this stuff, but you're building on work which they were doing and their selection mechanism. Is that something which is in your headspace? Are you thinking about permissionless systems?
I'm just thinking about just private chains. I mean, the guys at Ethereum are so much cleverer than me that I wouldn't want to even think about. I'm sure they're doing it properly. Yeah.
Oh, no more questions.
Okay.
Nice one.
Well, we're going to the pub.